Hello everyone, myself Subran Sipari, and here in this conference I am going to present the paper titled Study the Effect of Right Half Plane Zero on Voltage Mode Controller Design for Boost Converter. So all of you know that DC-DC converters are non-linear time-varying switching circuits which finds widespread application in different applications. It comprises of a MOSFET along with some control element, some controller, and basically it's the boost converter. Here we are considering the boost converter steps up the input voltage to a particular output voltage. The output voltage is greater than the input voltage with a moderate voltage conversion ratio. So the boost converter operates in three distinct modes of operation according to the magnitude of the inductor current, that is CCM, DCM, and the boundary condition. So the control objective of the boost converter is to regulate the voltage in spite of different load or line disturbances, parametric uncertainty, good transient performance, and ease of implementation. But one of the major limitations is that there is a right half plane zero in the boost converter transfer function, which reduces the bandwidth of the controller and produces the inverse response, which is a very peculiar challenging condition. And what we need to do is that we need to negate the RHP0 effect from the boost converter. So in this paper we are trying to find out the effects of the RHP0 and how to mitigate the system. Before going that, we need a circuit analysis. The first figure is the basic boost converter without any parasitic, but the second figure comprises of different parasitics. We have considered different parasitics. Here the steady state analysis, we have given the voltage across the inductor, the capacitor current, and the output voltage, and where Vmax, Vmin is there, and the output voltage for the non-ideal boost converter. The non-ideal boost converter, here we have considered all the parasitic elements, where D is the duty ratio, and the steady state inductor current triple, and the inductor expression for the inductor for the boost converter provided. And here we have considered both ideal condition as well as the parasitic condition. And for the component selection also, we have in the component selection we have also provided a minimum value of the capacitor of the boost converter, where we have considered the maximum permissible ESR, that is equivalent series resistor, for the specified output voltage. And there are also losses in the boost converter which can be conduction loss due to the inductor, capacitor, MOSFET, diode, and the power dissipation that are provided in equation number 9 to 12. Now coming to the main part, mitigation of RHP0. That mitigation of RHP0 can be done in two manners: either change the topology or change the controller structure. First is, and we will see both of that, and third point is that change the operating condition. Authors have suggested to use leading edge modulation of PWM generation, and they have also, some authors has also provided the region to reducing the switching frequency while converter is operating in CCM. And one of the most important feature is that the most important technique is that IAC, that is injected absorbed current. It is the method by which the RHP0 effect of the boost converter can be mitigated. And what is this IAC? It can be provided in equation number 13. And you can see the voltage mode controller of the boost converter, where we have used a controller using op amp and then the gate driver, and we have the gate driver. This is the PWM modulator technique. This one is the PWM modulator, where we have compared the controller voltage with the triangular wave. And here basically in frequency mode converter there are two different things, that is type 2 controller. Type 2 controller is a very 1, 0 and 2 poles, whereas, and here the figure number A shows the voltage type 2 controller, Similarly, type 3 controller has 2 zeros and 3 poles. And here the op-amp based representation and the Bode plot of the type 3 controller is provided. All the details of the mathematical analysis has been provided. Here in the simulation results, we have considered this as the input voltage is 5 volt and output voltage 12 volt. We have calculated the value of L and C, and substituting the values of boost converter, we get the G of S. But here you can clearly see the effect of, because the negative in the numerator shows the RSP 0. So for that we have used IAC method. Using this IAC method, you can clearly see that the RSP 0 effect has been nullified. And here, to strengthen our logic, we have provided the frequency response of the system, and GC2 and GC3, that is type 2 controller as well as type 3 controller, has been provided. And here the results of comparison between type 2 controller as well as type 3 controller are provided, where you can see that type 2 controller or the type 3 controller provides a much better and much faster response, and which can be seen in this comparative analysis, that type 2 controller and type 3 controller and TB is the total variation. And this paper provides the effect and of controller as well as the mitigation effects, the effect of RSP 0 on the dynamics of the controller design of boost converter, and as well as the different mitigation techniques for the same. And we have also provided the result mitigation technique, the best mitigation technique. We have provided the IAC method and the type 2 controller as well as the type 3 controller. This is for the boost converter, and these are some of the selected references of the same. Thank you for the